This morning I gave you a very broad, open talk about the engine and AIDA and the basic concepts, and I used some very embarrassingly simple examples like summing integers and multiplying them. And during this afternoon you've already done some more real-life situation where you've actually launched some calculations, an equation of state. But let me pull up the slides. This is still not fully representative of what we typically do in real life when we're doing science. And so that's what I'm quickly going to introduce now. I'm going to start, and then Espen is going to give some examples of how they applied those concepts in the aiida-vasp plugin. And what we've done so far, just a quick recap. The typical workflow structure that we've done so far, hope you can read it. I just took the example of what we did is the work function that runs an equation of state. We loop over some input data, so in this case the scaling factors. We create these structures and we launch a calculation for each set of inputs. So we launch a calculation and we use the results of each of those calculations in the next step for the analysis, and we call it a day. Except this has one big glaring mistake in the reasoning. It assumes that calculations never fail. As you probably know, this is not a realistic expectation. Calculations fail all the time. We of course picked these examples and these inputs that PW calculation converged without any problems. So we were safe in just assuming that the results were there and using them. Now, in real life, this is not the case. Typically, when you run a calculation, you will have to do something. You can put in a flowchart like this. Now, the flowchart and normal flowcharts might seem a little bit weird, but you'll see why next in the implementation. Typically, we start with some initialization, and then we have a while loop. While the calculation, we check if it's successful. If it's not, we prepare the inputs, we run a new calculation, and then we check for errors and handle them if necessary. And we continue this loop until this calculation has finished successfully, and then we attach the outputs. Very rough description. And so, in a workchain, you've seen now how workchains can be implemented with the outline where you can specify logic. You could think of doing something, implementing this in a workchain like so. So I've taken the PW base workchain. Basically, it's a basic workchain around the PW calculation whose job is exactly this. You ask it to run the PW calculation, and if it fails, try to handle the error and resubmit it until it actually does the job. And so here in the spec, you will see it does this initial setup. Then there's this while loop, which you should now have seen, and some qualifier like should I run the calculation, which probably returns true or false. We prepare the calculation inputs, we run it, and we inspect it. And until this condition is not satisfied, we keep doing this, otherwise we have the results. So now I would like you to think a little bit. What would you, so here in this inspect calculation, you would then look at the results of your calculation and try to determine if it got the result what you expected, and if not, how would you proceed? What would you do? So I don't want to, since this is an active workshop, I prefer we have one solution. I mean, this is by no means the solution. And so instead of giving you the answer, I prefer that you think about this tonight. And so for you, those of you who will join us tomorrow in the work group that will focus on the workchains, we can talk about this some more and we can discuss, and I'd be interested to see what kind of solutions you guys come up with, and we can see what works and what doesn't. And so that hopefully at the end, when you have your own ideas about how to tackle this problem, we can compare with what we did in aiida-quantumespresso, and we might learn something. In doing this, I think one key for tomorrow and when designing, thinking about workflows, the most important part is modularity. What I mean with this, that each workchain that you design should ideally tackle a well-defined problem. So before you start implementing, really start thinking, okay, what is this workflow designed to do? What should the inputs be? What is the logical pattern that it's going to follow, and what should its outputs be? And if you do this, basically the best thing is actually draw like a flowchart like this, and then translate it literally in the outline logic. Already if you do this, that will set you off in designing very nice workflows. And as well, create generic reusable components. So imagine you can have very simple workflows, like I showed you the previous one, that really its job is to take a PW calculation and run it until it actually completed the job. But this is still very basic. This has nothing to do with a high-level workflow of computing equation of state or a band structure that has to do multiple calculations, relax your structure, do a CF calculation and then a CF. So in this case, if you create robust components like a base restart workchain, if there you put all the logic that's necessary for error restarting, dealing with problems, the idiosyncrasies of PW, then your higher level workflows no longer have to do this. They can just call the base restart workchain, and they can be assured that it will take care of all the problems, and they can just focus on the high level stuff. It makes it a lot easier. Plus, you can then use this base restart workchain everywhere, and makes it very, you don't have to repeat yourself. So exactly, this is the example that I wanted to give you to illustrate this. A typical band structure calculation would relax your structure, which will often do multiple calculations, might do some meta convergence on the volume to make sure it's not in some metastable state. Once it's relaxed the structure, will generate the charge density through an SCF calculation, and then finally integrate along the high symmetry points in the Brion zone. And in the case of PW, all of these will need to run PW calculations, all of which will most likely suffer from similar problems. So instead of dealing with those in your band structure high-level workflow, we make this base workchain. So all the nasty and difficult stuff is now taken care of by this block, which means that your relax and your band structure doesn't have to deal with this anymore. This is a bit the idea of compartmentalization. Really define the responsibilities and create reusable blocks, and then make your high-level workflows very, very simple to implement. To show you, this is what the PW-based workchain actually looks like in the aiida-quantumespresso plugin. So here you see its specs. I've only included the inputs, and essentially these are only the inputs that PW calculation in principle needs. You see the code, structure, k-points, parameters, etc. And so the logic also there will be just focusing on the error handling. So now if we want to define the relax one, the relax needs to provide the option to also specify these inputs. Now this is the problem I faced when I started implementing this. If I implement my PW relax, I had to copy paste all these inputs essentially, and more for the relax, which is not very nice. So I came up with this solution that's called exposing of the inputs. And so instead of now, if you look at the implementation of PW relax workchain, instead of having to copy paste all these inputs to allow someone to pass those specific ones, I hope this is readable. I will send you the slides. It's called expose inputs, and I just define that it exposes the inputs of the PW-based workchain. Now AIDA will magically expose these inputs for you. And then I can just focus on the inputs that are important to the logic of the relaxed workflow itself. So here there's some inputs to do with the meta convergence if I want to converge on the volume, etc. And even when we go in that next step to the bands workchain, you would think now I have to copy all those inputs again from the relax, from the base, but nothing. That's not actually the case, because due to expose inputs, these are just 3 lines. We expose the relaxed workchain inputs in the namespace relax, and we do the same twice for the base workchain and SCF and bands. Now, what this would look like if you then actually have to pass those inputs, looks something like this. You've already seen with the builder how you can specify inputs, but you can also use a normal dictionary, and this dictionary now will follow the same structure as you've exposed your inputs in this high-level workflow. Which means that now, even though the base workchain that runs this calculation is nested 4 levels down, if you want to say run the relaxed workflow with a low k-point density, because you don't need it to be that strict, you now have the freedom. This pointer's not really. You have the freedom to say, okay, for the relax workflow, I want to use this density of k-points. But for the SCF, I actually want a slightly more dense grid. And for the bands, even denser. And this goes for all these inputs. You have access to all these inputs all the way, no matter how deeply nested you are, without having to actually copying all those through the expose inputs. So this is a very simple tool that stimulates you to make these sub-work chains and use wrapping workflows, and then through these expose inputs, it doesn't cost you a lot of copy pasting and actually makes it very transparent. And so what would this look like in the implementation of the band structure workchain if I, for example, now want to launch my relax workchain and get all these inputs that were passed by the user? There's a very simple method called exposed inputs, and I define again the name for which workchain, so in this case the relax workchain, and the namespace that I expose it in. And this will return this dictionary of inputs. So I don't have to go manually searching from what did the user actually pass. And then it's a normal way of submitting, so I call self.submit with the class and the inputs. So with these simple few tools and infrastructure, even as something as complex as sub workflowing and making all these different layers, makes it still really usable and manageable for an implementer. All right, so there's hours to talk about this in the implementation, but I don't want to bore you too much. So I'll now give actually the word to Espen, who, as I said, has used these principles in the VASP plugin to write some actual more advanced. Some of it, at least. Yeah. It's okay. I'm just a bit slow. Okay, this is fine. So this is the pointer. Very well. Yeah, but this is fine. I'm not gonna actually use the pointer, I guess. So I'm just gonna be very brief. This is late, as we all know. And what I'm gonna talk about now is kind of one approach on how we could look at the sort of overall problem of doing computations, especially in material science. That does not mean that's the only solution, because there will always be exceptions and people would like to do all kinds of custom things. So don't get offended if this looks like a very restrictive box. At least up until now, current status is that we now have a nice Python interface to your code, if that's not in Python already. We have the data provenance. Possibilities to do error handling, well, we haven't really talked too much about that yet, I think. So this is something we should talk more about tomorrow, possibly. But to be truly useful in science, we need to do more. So we need to increase productivity, and that doesn't mean necessarily quantity, it also means quality. And we need more rigid way of performing computations, data analysis, and a point that I find very interesting, that should be less possibilities of shortcuts. Scientists love shortcuts, and if they find one, they use it brutally. So if we can kind of structurize this in a way that this is only possible if you really want to do this, I'm sure we will have a little bit better results and better productivity. We want more time to analyze our results, interpret them, and of course design new studies. We want to do science, right? We want to discover new problems. We want to solve the problems, etc. We won't necessarily do numerics. I mean, some of us love numerics as well, but depends. And we also want new novel ways to traverse domains. So in material science, they would typically be multi-scale type of things, which is only really realizable when you have a framework which can couple codes, input, outputs, and of course, in the end, also metadata type of things, which is also going to enter at some point. And possibilities of utilizing different codes for different purposes, and ideally, these things should be made independent of the code, so that you could utilize it on different codes. Of course, this is not always possible. So typically in science, you have a pool of samples. If you're an experimentalist or a calculation guy, it doesn't really matter. You pick your samples. In this case, you're a calculation guy or girl. You do your calculations. You get some results. So this is one way of doing it. Or you pick a sample and do a series of calculations and you get the result. Or you do the combination of those. That's kind of like the thing. And also, sometimes you feed back to the sample pool, right? So this is rather trivial, but then you get an overview of how we work, right? Everyone has probably seen this before, huh? And then, so now I want to take a little bit of an example from this side that we used in VASP, where we put together a sort of a chain of workchains into a workflow. So we designed this package. So we start with the structure. That's kind of our sample, the blue guy here. And this can, of course, have been generated by another previous workflow or a parallel one or something like that. We have a restart workchain, which Sebastiaan talked a little bit about, or the base workchain, which does a lot of the sort of backbone things. And that's, in theory, independent of code. At least that's the idea of it. And then on top of that, we have the VASP workchain, which converts your workchain inputs into the or outputs into sort of the VASP calculation specifics.
So this is typically where you want to have your quantum espresso workchain if you want to use that. Then we have the verify workchain, which basically has the possibility of checking physical principles outside of the numerics. Sometimes you want to do this, either restrict something or just double check things. This is also decoupled from the code. We have, of course, the relaxation workchain and the convergence workchain. Typically for material science, this would be, and the plane wave codes, this would be the plane wave cutoff and the k-point grid, right? So none of these are really interesting in science. I mean, this is, to some extent, this should almost be a black box. And coming back to what I said first, don't be offended by that, because I don't really mean that, but let's think about that for a while. So it's mostly numerics. The material scientist shouldn't need to worry too much about this. There's probably a lot of error correction going on here, automatic restarts, fixing problems. We all know how this is when you run this type of computational clusters. I'm not kidding. I think most of us spend most of our time restarting calculation, fixing problems, trying to understand what went wrong, right? And usually you do the same thing multiple times. Sometimes you even forget what you did the last time. We all know this, right? So let's try not to do this again, at least in the long-term future. Yeah, right. So this stuff should, in principle, be independent of the code, right? Except this guy here, which we have called VASP. And also the technique used, whether you use DFT here or GW, whatever, shouldn't really matter. So here's where kind of the science happens, and here's where we should spend time, right? Here is where we should inject the interesting workchains. Here is where we should spend time designing new studies, right? To do extract bands, equation of states, transport properties, all kinds of things like that, structured dynamics, whatever, you name it, right? And couple the things. And in numerics, you typically have this term of refactor code that's kind of like established these days. So I would say we should refactor science as well. And I don't know if anyone of you guys are involved in engineering, but there's this lean engineering, which is kind of becoming well established now. And this is kind of related to this, to refactor the problem and optimize the things you can optimize and kind of free up time to do the things that are really important to obtain progress. And of course, try to make this scientific workchain as reusable as possible. And this is important when we do this together. There's no point of one of us sitting to developing a workchain and another one is doing more or less the same, right? So we should try to generalize this as much as possible. And for us, I think, especially for the plane wave community, where the codes are so similar, I think that's a very nice place to start. For instance, with VASP and Quantum Espresso, Abinit, and this type of things. If we could manage to do it somewhat there, and I believe it's possible. We only need possibly an input wrapper or something like that, and some other things. And at least for a few standard calculations, this should be possible. And then you can exchange the code and do tests and, of course, do the stuff that was talked about this morning with respect to the accuracy and precision tests. And the plugin, yeah, so this is what I said. So now we're just going to take an example from this convergence workchain that we have. So now I want to ask a question about how many are actually doing this convergence test for all your calculations, right? Yes. I don't do it for all my calculations. I did it the first year, but then I kind of stopped doing it, right? And how do you escape the problem? Well, you just jack up the parameters, right? Well, these guys should be okay. But then you waste a lot of resources, right? This makes no sense. And if you're going to do... Well, yeah, we can discuss that, but okay. And then you waste resources. And if you do high throughput stuff, this is not really very efficient, right? So we should be able to perform this convergence test for relevant parameters. Like, okay, so if you're looking at the band gaps, you would like to look at how your band gap converges. So the total energy is not necessarily the thing you want to study, right? And, well, this is what I said. You shouldn't harden the result more than necessary. Not jack up the parameters. And you also need a relative convergence test. That's what I said with the band gap. So say, for instance, if you do displacement in a structure, for instance, you would investigate how the relative band gap changes as a function of the convergence, because that's what you actually want to study. And then you could, of course, think of a huge matrix of these type of things, and then define that in your Convergence work chain, and then the user selects whatever they would like to study, and then kind of this goes automatically, hopefully. So let's look a little bit on this work chain, because now you already worked a little bit with this outline, right? And this is probably a little bit longer than the stuff you've seen until now. I'm not going to spend too much time on this. Basically, we just first we do a plane wave convergence thing. That's kind of what you need to do first, because you have a better understanding of a reasonably dense, of how your k-point grid is supposed to be, as opposed to the plane wave cutoff. So you do that first, and you do the k-points, and then of course you do the. So here we only do the displacement and the compression of the cell, the difference, and then we do it on the band gap, the total energies, the top of the valence band maximum, and another parameter I actually don't remember, and of course then we analyze the result, we store it. And then in the end, of course, you want to run the calculation with the optimum plane wave cutoff and the k-point grid. And typically, you would interpolate that data. So you set a cutoff, and you interpolate the data you have, so you get the precise plane wave cutoff that you want to do. This is not so easy with the k-point grid, obviously. So that's why you typically would like to do this instead of just looking at take the combination you already have from your data. And then Sebastiaan already mentioned this with the expose inputs and outputs. So I'm not going to mention that.
I'm sorry.
What?
I spoiled it for you. I cut the grass away from you.
Spoiler, yeah. Well, that's how life is today, huh? Okay, so this is fun. So this was just a sort of brief introduction to how we do this in VASP. We kind of see this as a kind of base workchain package for us. And I think a lot of the stuff that we would so a lot of the scientific workchains, if you would like, would be injected here and would call this stuff. Obviously, you can skip a couple if you wanted to. If you want to extract the band structure, you don't want to do convergence in a relax unless you will have done it. Just use the data you have, etc. And of course, when you do this stuff, in the end, we would also like to utilize the data you already have. So for instance, if you do a defect, it makes sense to start from some base data that you already have and just fill in the points if need be and these type of things. So yeah, that's it. I think there's a lot of potential here. Yeah, or pseudo potential or whatever. Yes.
So. I've never actually looked at the VASP invitation yet, I have to admit.
Yes.
So is this stack, we talked about sub-workflowing where you workflows in another. Is this the case? Is the converge wrapping the relax, which is wrapping the verify, which is wrapping the VASP, or are these consecutive work chains? So if you want to, you first do the converge, when it's done, then you go to the relax, and if it's done, you go to the verify. So is it sequential, or is this
no, so the converge one can submit several relaxation ones, for instance.
Okay.
So we just do a submit on each of these. So they're kind of separate. So we don't inherit. Like
but the relax, verify, VASP, those are done on the same level.
Yes. So what do you mean now? So what, these two guys? No. These two?
So it's clear, the converge is wrapping all the green ones, in a sense.
Yes.
It's sub-workflows, not sequential. But then for relax, is the relax also then each relax calls the verify, and that each verify calls the
yeah, but you can skip it if you want, yes.
Yeah. But that brings me to my next question, because you say the VASP there is the one that puts in the specific knowledge that is relevant to VASP.
At least that's what I would like it to be, yes.
Okay.
Yeah.
But the converge, as you also said, converge which parameters you might want to converge.
Yes.
Also depend on what code you're using.
Right. So in the long-term perspective, what I would like here is an input wrapper, where we, because say for the plane wave codes, I mean, you know the input parameters, right? Irrespective of what they're called for the respective codes, you know, like the plane wave cutoff, the k-point grid, whatever it's called in the respective programs. So then we could use those variables, and then the input wrapper just looks at the entry point for the plugin you want to use, and then sets.
Okay. So one of the inputs will be say, okay, use this code deep down.
Yes.
And then when it gets there at the VASP block,
Yes.
We'll look at this value, and
Yes.
if it's not VASP but QE,
Yes.
we'll swap to QE.
Yes, yes. This is what I kind of would like it to be. Yeah. But we're not. This is not implemented. But this is something I think we should look at with the quantum espresso thing.
Developers have to get together. And
yes, I think so.